Hello everyone. In the previous video we have seen one of the uninformed search algorithm called as breadth first search. Today we are going to see one more algorithm called as uniform cost search. In breadth first search, one of the assumption which we made is all the step costs are equal. What if the step costs are unequal? What if there is a weight at each edge? What would be the best path to reach to the goal node? So uniform cost search helps us in finding out that best path starting from the starting node to the goal node. So we use a cost function to quantify or to compute the total cost incurred at each node. And at each stage, when we compute the cost at each node, the cost to that node is the optimal. So we will discuss more about that. And uniform cost search is actually a variant of Dijistra's algorithm. Dijistra's algorithm also attempt to find out the shortest path from a node, source node to the goal node. But there we explicitly need to have the information of all the vertices, and whereas in uniform cost search it slowly increases the queue and we try to reach to the goal state. In fact, since uniform cost search goes slowly, increasing without actually explicitly storing the whole of the graph, there is a lesser requirement of memory in uniform cost search as compared to Dijistra's algorithm. So, the idea in uniform cost search is we have all the nodes and we try to compute the lowest path cost from the initial state to that particular node, and we call that as this g of n here. We use priority queue as the data structure. If you remember, in breadth first search we have used first in first out queue, whereas here we use priority queue, which means that the one which has the lowest cost would be popped out. The node one which has the lowest cost would be popped out. So there are fundamentally two major differences between uniform cost search and BFS. So the important difference is we don't test the whether a particular node has reached goal or not once a child is generated in uniform cost search, whereas in breadth first search we do that. I'll show that in the pseudocode more elaborately. So in breadth first search, once a child node has been generated, we immediately test if it is a goal node. If it is a goal node, then we close the algorithm and we say that this is the best path which can be reached to the goal node. Whereas in uniform cost search, we try to go through, we try to, uh, we don't do goal test immediately after generation of child, whereas we do it at some other point. So we'll discuss that in pseudocode. And we also see if there is a better path uh, for a particular node, and if at all if it is there, we try to replace it in frontier, which we did not do it in breadth first search. In uniform cost search, in the frontier, whenever you have a better path, you try to update a node for it. In breadth first search we used to ignore it. We actually don't do that, whereas in uniform cost search we try to update the cost with the lowest, update the node with the lowest cost. So let us see how uniform cost search and breadth first search differ. So these are the two pseudocodes of breadth first search and uniform cost search. In breadth first search, we have seen in the previous video that goal test happens immediately after the child generation. If you can see here, the one which has been highlighted in the red, so in the left side, if you see, we after the child has been generated, we see whether it is present in explode or frontier. If it is not there, then if it is not there, which means that we try to test whether it is a goal node or not. We don't do that in the uniform cost search. There is a particular reason of why we don't do that, because if you do that, we will not get the optimal lowest path cost to that particular node. I'll show with one example to discuss this point. Instead, we try to test the goal node immediately after we popped from the frontier. So that's where we try to do it. This is one of the difference between breadth first search and the uniform cost search. So now let us see how uniform cost search pseudocode works. So this, as we can see here, we have the complete pseudocode, and let's try to apply uniform cost search for the graph which is given here. So here the node A is the initial node and G is the final node. We would like to reach to the node G with the lowest cost, and we have all the terminology: frontiers, explode, and children. So let us start. So first we try to extract the node, and so here the first step says that we should get the node as the initial node. So and also we place that into the frontier. So a periodic queue ordered by the path cost with node as the only element. So first node will be A here, and also frontier will also be having node A. So currently explode is 0 and there is no children we have generated. So the loop starts here and we test if the frontier is empty. No, it is not empty. If it was empty, we could say that failure, we did not reach to the goal state. But here it is not empty, so we pop the first node from the frontier and keep it in the node. We already did it. So here we test whether this node is a goal node or not. A is not the goal node, G is the goal node, and so we add this A to the explode. So that we do it, and once we do that, we check for the children of the node A. So as you can see here, node A has B and C as the children with path cost 80 and 99. So we try to place the first child, which is B, and so we try to, once the child has been generated, we see whether it is already present in frontier and explore. It is actually not there, so we place that in frontier. So the node B, we will also just note the cumulative cost, which is 80. So if you see this node is a actually a an object where we actually store these path cost and various other states. If you remember, in the previous video we have seen various state from which parent it has come, what is the path cost, all those things would be stored. So I'm just representing in this way. So B has a cumulative cost from the initial node as 80, so that has been placed in frontier. Now once that has been done, so we check. So since this is else if, so we don't need to go here. So once this is done, we try to go for the next child. The next child is C, so C should actually replace this B earlier, because B, so now child would be C, and we also see whether C is already there in the frontier or explode node. It is not there, so we can place C with the cost 99 here. So once again, we don't go here, because we go here only when we have only when the node is actually there in the frontier, and if at all, if we have a better path cost, we try to update it. So this else if is, we go to else if only when there is a already the node is present in the frontier and we try to update with the lowest cost. But in this case we don't have it, so we place C node with the cost 99. So now once we have generated both the children, we go back to our top node and we extract, we pop once again frontier. So here the important thing is, when we are popping the frontier, it is not a first in first out, it is a priority queue. So the one which has the lowest cost would be popped. So I forgot to remove this. Earlier we have already popped it, so this is already gone. So now we are trying to pop B, because B is having the lowest cost. So just erase this here and place it in the node. So here in the node we are placing B 80. So this is the current node, and this node is going to be also be placed in the explode node. So we will be placing that B, and so this B node, let we'll be seeing what all child it has, and also check whether it is there already in the frontier or not. So if you see the B node, it has only one child, which is D. So let's replace the child here and with D. So now the child is D, and this D child, we have to check whether it is in frontier or explode. It is not there, so you can update D with the total costs incurred from the beginning. So here 80 plus 97, which is 177. So 177 is the cost, and so that is being placed in the frontier. Now we also see there is no other child, so we go back to the loop once again, and we try to pop the next node, which is C99. So we erase here in the frontier because we are popping it, and we also erase the node, and we try to place here the cost of, so C99 as the active node. So now this C is also placed in explode, and this C we will look for the children is G. So this is the important thing. So here now child is G. Let me write it first. So we have G as the child. So this G is also the goal node, but we are not testing the whether it is a goal node or not here. If we have tested it, it would have stopped here, and we would have said that 99 plus 211. So 211 plus 99, which is 10, 11, 310. 310 would have been the cost if we have tested the for the goal node at this point immediately after generating the child. But uniform cost search does not do that because it does not give you the optimal path. I'll show that why it will not give you the optimal path. So currently the child is G, and we are checking whether this child is already there in the frontier or explode. It is not there, so you can place that here in G node, G with the cost of 310 in the frontier, and this once this is done, you actually go to the next loop in the and pop the lowest one. Here the lowest one is D177. So let's clear that D177 from frontier and place that in the node. So D177 is the current node. So this D177, we also place this D in the explode nodes, and now the node D, we will see what are the children for it. The node D has a child as G. So we already had cost. So we see when D has generated the child as G, the G is already present in the frontier here with the cost of 310. So this condition will fail actually. So this if condition will fail, and we will go here and and we try to see the cost, the total cost. So if you compute the total path cost until G through D, it would be 177 plus 101, which would be equal to 278. So G278 is way less than G310. So this 310 would be replaced. Here the G310 would be replaced with G278. So in this way, the lowest path cost, since we have waited for one more round to complete, we were able to find out the lowest path cost to G. If we had tested for the goal, if we have done goal test immediately when we see the goal node, we would not have got this 278 as the path cost. So let us see how it goes. Now once you got this goal test, once we have replaced the node with the updated cost, so we go back here, and we try to pop the next node is G. So this D would be replaced with G, and the G would be G is 278 as the cost, and this G next immediately will test for the goal test. So this is where it gets satisfied, and this condition will satisfied, and we reach to the goal node. So in this way we try to reach from A to G in the lowest path. So the important difference is in breadth first search, immediately after generating the child, we have actually tested the goal test. That's what we have seen when I have compared. I've highlighted in the red portion. Whereas here we don't do that. We instead wait for all child to be generated, and then we will be going back and popping the node, and then we try to test it. So in this way we find the lowest path cost for the uniform cost search. So now let us see what is the cost incurred in uniform cost search. So uniform cost search is optimal, which means that the path which it gives is the best path. There is no better path than what we get from uniform cost search. And so there are two reasons why uniform cost search is optimal, because if we reach to a node in uniform cost search, uh, and if it is about to be generating its children, which means that that particular node has reached its optimal path. So that is what is written. Whenever uniform cost search select a node for expansion, the optimal path to that node has been found. Also, we assume that there are no non-negative. There is no all the costs are non-negative, which means that there are no negative costs. So using these two conditions, we can say that uniform cost search will always provide you the optimal path. And also, to find out the time complexity, so here we don't represent the time complexity in terms of number of branching factor and the depth. Instead, the total cost incurred, the path cost incurred, and the edge. We always assume that there is a small positive constant epsilon for every edge. So if we divide the total path cost divided by epsilon, we will come to know how many at most, because we are analyzing the worst case. So at most how many steps or edges it could have. So that's how we reach to this. So we divide C star divided by epsilon. C star is the total cost, epsilon is the smallest cost positive constant. So when you divide it, it is way above. So it would give the total number of edges, and so this is way above than b power d, which we have seen in the previous breadth first search. So that is the cost. And so the uniform cost search, which is UCS, actually not USC. So UCS is actually a when you choose all the path cost as uniform, UCS will become breadth first search. So BFS is like a special case for UCH, uniform cost search. So this is the time complexity of uniform cost search. It is also both optimal and complete. So when we say complete, it means that it is going to find the solution to the goal node, and optimality says that it is also going to reach with the lowest path cost. And we have seen the time and space complexity, both are very huge, and we represent in terms of cost, total path cost divided by the epsilon, which is the smallest cost of in particular node. So in this way, breadth first search and uniform cost search, when we compare, both are similar. Slightly more uniform cost search is more costlier in terms of time and space complexity, but uniform cost search is more generalized, because the path, the edges or the paths can be non-uniform, and we attempt to find out the lowest path cost to the goal node from the initial node. Whereas in breadth first search, we assume that all the nodes, all the paths have the uniform cost. So this is about uniform cost search. We will see the next algorithm in the next video.